Hi, I'm Meredith. I'm a dietitian. Probably not your dietitian, so please consult with your own personal healthcare provider before you make changes to your diet, your supplements, your medications. This video is about lipid membrane damage and also plasmalogen deficiency. And I think that's the end game in anhydroretinol toxicity, but also in any type of high reactive oxygen species situation. So not everything is anhydroretinol. As I'm sort of an extremist nutritionist, so I'd be like, it's anhydroretinol, but it can be not that. It can be oxidative stress from anything. So oxidative stress can destroy lipid membranes. So let's go and look at this. One of the signs of destroyed lipid membranes is problems with memory. So sometimes when I say, I'm very worried that it's my lipid membranes. So if you go to part 2 of this series about mitochondrial madness, you can watch me go through what I think is happening when someone is in anhydroretinol toxicity. So I'm not saying that vitamin A is all, like, toxicity is all anhydroretinol. I do still think that you can have excessive amounts of retinol aldehyde. There can be like a block there. I do believe that some people can get retinoic acid toxicity. I don't think that that happens to everyone. It's not the only way to become toxic on vitamin A. So I think anhydroretinol explains so much, and the fact that we actually make this in our body means that it's a potential toxicity for people who are unable to deal with the amount of anhydroretinol that is made normally in metabolism. And then I also believe that some people are making it in their gut due to excess amounts of alcohol being produced by gut dysbiosis. And also, if you drink alcohol, you likely make anhydroretinol. That's probably why people who have alcoholic liver disease don't have vitamin A in their livers, because you can't store anhydroretinol. You have to rehydrate it to rehydroretinol. So very interesting, right? Okay, enough babbling. On to this. So whenever anhydroretinol takes the place of retinol in the PKC delta signalosome, then we have a problem, because pyruvate dehydrogenase complex gets turned on and it stays on. And that can lead to multiple downstream effects, such as B1, lipoic, B2, B3, and B5 deficiency. So here's something interesting. Have you ever had a paradoxical effect from starting a supplement? Have you ever felt way, way worse? Well, maybe it's because your underlying problem is that you have anhydroretinol in your PKC delta signalosome. Just my own personal experience, I'm not bashing high dose thiamine, just talking about it, my own personal experience. I started high dose thiamine in 2020 because I was having problems with GI motility, and I was having problems with esophageal dysmotility. And so I decided to try that because I wanted to hack my acetylcholine. And so it did help, by the way. It did that, and also bicarbonate helped to restore my esophageal function. Everything started moving again. So, but I continued on high dose thiamine for 2 years. And then my pain was so horrible. It was over the top. I had to do dry needling for my muscles. I couldn't barely function. I was diagnosed with fibromyalgia because they could not find, small fiber neuropathy. They couldn't find neuropathy, right? So you just have fibro. I think it was because I was reactivating my pyruvate dehydrogenase complex. And I believe that I do struggle with anhydroretinol. So yeah. Okay. Anyway, moving on. Is the pain better? Yes. Do I do high dose thiamine anymore? No. When I do, I get worse. So I do use benfotiamine, but I use about 30 milligrams a day, not high dose. Okay. So whenever you're struggling with this pathway, what ends up happening is you have an excessive amount of hydrogen peroxide or hydroxyl radical or superoxide, and all of these reactive oxygen species can cause damage to your lipid membranes, okay? So lipid membranes are crucial for cells to work and also for the mitochondria work, because mitochondria have lipid membranes too. So here's the outside of the cell. It's made up of the cell membrane, and this is called a phospholipid bilayer. And I actually love that word. It was like my favorite thing to say in college. It's a phospholipid bilayer. So what it is you have these phospholipids. So the phosphate group is here on the outside, these little balls, and then you have these lipid tails. And the phosphate group is hydrophilic. It loves water. Makes sense because on the outside of the cell, there's water, and then on the inside of the cell, there's water. But we need something to act as a barrier so that not everything can get through all the time. Some things we allow to go through, excuse me, by simple diffusion, but some things require transporters, and you can see these little transporters here. So the inside of the membrane is made up of fatty acids, and so those are, sorry, I just heard Zoe in the background. She's waking up. Okay, so those are actually hydrophobic. Okay, so they don't like water, and that's why they're kind of stuck together in the middle. They stay away from the water that's on either side of the cell. So we don't want these guys to get damaged with oxidative stress. Luckily, we have a nice enzyme to help to deal with that. It's called ALDH7A1, and I have a video on that about how ALDH7A1 is a moonlighting enzyme. And if it's busy dealing with your oxidative stress, then it's not metabolizing lysine right. And bad lysine metabolism produces P6C, and that can cause a B6 deficiency. And if your B6 is non-functional because of P6C, then you won't be able to make GABA. And then that, excuse me, that leads to the inability to upregulate all of the things that you need to be able to get rid of the peroxides and the hydroxyl radicals superoxide. Okay, so super important enzyme. And B6 is needed not just to make GABA in the liver, but also in the brain. And in the brain, GABA is, let me take a sip of water. So in the brain, GABA calms the brain down. Glutamate to GABA is B6 dependent. Glutamate is neuroexcitatory. So many of my clients have seizure disorder. And a few of them definitely have anhydroretinol toxicity. And I think that it led to this functional B6 deficiency, and it triggered seizures. So here are reactive oxygen species, and they actually initiate lipid peroxidation. So you can see here's a hydroxyl radical, and that causes a lipid radical. And then there's propagation. The lipid radical interacts with oxygen, and it causes more radicals. And then you end up with a lipid peroxide as well. And then these lipid peroxides are 4-HNE, ACR, and MDA, and they're metabolized by ALDH7A1. And this is NAD dependent. So you require NAD to be able to work this enzyme. So 4-HNE causes macular degeneration. The eyes are not just the window to the soul, they're the window to lipid peroxides. And then also 4-HNE has been shown to cause seizure disorder. So there's a lot of connections here. And we can connect this back to any type of reactive oxygen species, but definitely anhydroretinol is a suspect in this, as I see in my clients that their vitamin A in their blood is spiking sky high. And I do think I probably know a whole nother video about what I think is happening there. I do think it's because just overall there's too much vitamin A, but then also I think that their body is trying to go in protection mode to potentially hold on to the retinol so that they're not making excess anhydroretinol. Very interesting. Lots of theories. So possibly a functional B6 deficiency when you're having a lot of oxidative stress. But what if, you're damaging all your lipid membranes? There's one lipid that we make called plasmalogen, and it is an important one for sure. And I've loved researching this. This has been mind-blowing to me. So there's two plasmalogens that we make. There's plasmalogen ethanolamine. Sorry. And then there's plasmalogen. So ethanolamine and plasmalogen. The Texan in me wants to say ethanolamine to match with choline. So if I say that, forgive me. You know, one of my kids said, "Mom, when you say things wrong and I learn it the wrong way, then I look stupid." And I was like, "Oh, sorry." All right. So biological roles, ion transport. So to be able to transport ion forms of nutrients, so like zinc ion, magnesium ion, all of these things, you require plasmalogens for the membrane. It helps with signal transduction. So we can think of that as like neurotransmitters or signals within the cell membrane to trigger things in the cell. It actually holds on to secondary messengers. So it's reservoirs for secondary lipid messengers, membrane vesicles. So there are specific membrane vesicles for things like serotonin, dopamine, norepinephrine. Those require VMAT. And so to be able to get those into your cell so that they actually work, you require membrane vesicle. Synaptic transmission is affected by low plasmalogen levels. So it could affect your ability to move your gut. It could affect your ability to learn because a lot of those things require synaptic transmission, of course. I already talked a little bit about neurotransmitter homeostasis. You have to have this vesicle and it's, if plasmalogens are low, then those don't work very well. Also the regulation of fusion and fission. So whenever your cell mitochondria are whenever they get too much oxidative stress, what the mitochondria does to try to keep the cell from dying is mitochondria splits and you make two baby mitochondria. And then you have to remake all of the complexes that sit in the membrane, and you have to make a new PKC signalosome. And so I think part of what's going on for people is that there's only a certain amount of PKC delta inside of a cell, and that gets sucked into making the new mitochondria. And it's a way to regulate oxidative stress, because if the entire mitochondria has so much oxidative stress, then that will signal apoptosis for the cell. So plasmalogens are involved in that signaling to start a new mitochondria. And interestingly, if you go low on PKC delta, it's been shown that it causes mast cell degranulation. And a lot of the people that I know are struggling with mast cells, like they're just struggling with massive histamine issues. And maybe it's because they're making a lot of baby mitochondria and sucking their PKC delta into that. Okay, so the last thing I'm going to say, because you know I'm a talker, is the important one that we're talking about today. Plasmalogens, they're antioxidants. They're really good at sucking up reactive oxygen species and reactive nitrogen species, which I don't really focus on very much, but that's another damaging thing. So I think that plasmalogens are our brick wall. I think it's our last stand. I think that when you have so much oxidative stress that you can't deal with it, then you just use your plasmalogens to mop it up. So the reason why this is such a good antioxidant is because of the special vinyl ether bond. And so what it does is it has these 3 locations that can mop up the reactive oxygen species, but it doesn't propagate. So it doesn't do a domino effect where it passes on the or sucks up more oxidative stress and becomes a lipid peroxide. It just sucks up the oxidative stress and it's at a standstill. And then the body can break this down with enzymes. Okay. And so what is it made of? Well, you have to have a phosphate group. So if you have high phosphate levels, I mean, that could be diet related. You could have very high dietary phosphate. It could be kidneys aren't doing well. You could be holding on to phosphate, but it could be that your phosphate is high because you're breaking down plasmalogens pretty fast. Okay. So that's theory. I haven't proven that in a lab, but it makes sense in my mind that that could be a cause of high phosphate levels for someone. Okay, so you have a phosphate group, and bound to that is choline or ethanolamine. And then there's this glycerol backbone that's super important. You have glycerol to make this molecule. And then you have a fatty acid over here. And this particular fatty acid is usually a polyunsaturated fat. And then you have the vinyl ether bond with this oxygen right here. And then this fat, R1, is usually a saturated fatty acid or a monounsaturated fatty acid. And so the important thing to take away from this is that we need saturated fat, monounsaturated fat, polyunsaturated fat. But where you get your PUFAs from is important. It shouldn't be seed oils because seed oils are already damaged from an oxidative stress standpoint. So it should be whole foods. You could get your PUFAs from, seeds, pumpkin seeds. That's one of my favorites is pumpkin seed. Okay, so that's important. All right, so let's talk a bit about diseases with plasmalogen because I think anhydroretinol causes problems with plasmalogens, but here are particular things that can happen. There's a syndrome called Zellweger syndrome, and that's where they have a problem in their peroxisomes. That's the beginning part of making plasmalogen, and it happens in the peroxisome. That's the first part of it. So what they have is they have a really slow DHAP enzyme, this enzyme, it's DHAPAT. And so their DHAP is low, and that's a precursor for making a plasmalogen that comes from glycerol, okay? So that ends up causing a deficiency of plasmalogens. Then another disorder is Parkinson's disease or Parkinson's disorder, because it's really an umbrella term for symptoms. And so what they find is that people have a lot of oxidative stress, and the oxidative stress causes a deficiency of plasmalogens. They're tied up in oxidative stress, and then there's impaired neuronal transmission. And then this particular issue is multiple sclerosis. And in MS, there's a higher immune activity, and that causes increased reactive oxygen species, and that reduces the amount of plasmalogens. Okay. And then you have myelin sheath degeneration. So I think that anhydroretinol could cause a problem there as well. Obviously, reactive oxygen species, oxidative stress. I also think that anhydroretinol decreases DHAP. So I'll show you that in a bit. All right. And then we have Alzheimer's disease. So Alzheimer's disease has a reduction of plasmalogens, and it's because there's a shift in function. There's more very long chain fatty acids being made, and then that means less shuttling of lipids towards making plasmalogens. So yeah, so those are 4 disease states. So what about us, like or me or anyone who doesn't have these specific issues? Okay, if you don't have those specific issues, what are some other symptoms that you might be struggling with plasmalogens? Okay, so if you have very low cholesterol levels, you likely are struggling with plasmalogens, because plasmalogen deficiency can cause low cholesterol. Now, plasmalogen high levels in the cell apparently can also cause low cholesterol. So you would then just have to kind of look at the person and their diet and determine, like, if their diet's very low in choline, most likely they have low plasmalogen levels. Okay, so okay. If you have reduced, you could have symptoms of reduced monoamine transporter 2 or MAT2. Also VMAT would be another name for this particular monoamine transporter. And that would cause disruption of dopamine, serotonin, norepinephrine, and histamine. If you can't uptake histamine into a cell, you can't get rid of histamine. The machinery for breaking down histamine is not inside the blood, it's inside the cell. So if you're struggling with histamine intolerance, this is probably a contributor. Potentially, you're having a hard time with your monoamine transporters or other transporters that can also put histamine into a cell. If you're struggling with dopamine, serotonin, or epinephrine, then it could be low plasmalogen. So the struggle with these transporters causes neuropsychiatric disorders like insomnia. I started recording this video at 3 a.m. Anxiety, bipolar disorder, schizophrenia, autism, depression, and Alzheimer's disease are all symptoms of having struggles with these particular neurotransmitters. Very high cholesterol levels could also be a sign of not making plasmalogens, mostly because you're pushing your lipid production towards making lipids rather than making lipid membranes. So that's an issue as well. Also, the phosphatidylcholine is being used to make VLDL. That's in the video number 3. It's being used to make VLDL instead of phosphatidylcholine being used to make the choline version of a plasmalogen, right? So, oh, and I already said histamine intolerance. So histamine intolerance is a huge sign, I think, of plasmalogen deficiency. You have to get histamine into a cell before you can start to break it down. So how do I think anhydroretinol fits into this? Again, any type of oxidative stress could cause problems with plasmalogens. This is actually my second map of this. So I tried to simplify it a little bit because, I like to make really big, crazy maps. So I simplified it a little bit, and we're going to go over it piece by piece. And I will try to just load this onto my blog. I'll put a link in the description so that if you want to look at it closer, maybe you're on your phone or something. Okay, so let's start here. Anhydroretinol or beta-apotencarotenol could cause a pathological PKC delta signalosome. So beta-apotencarotenol, if you go back to the first video in this series, so this is actually a product of the beta-carotene monooxygenase 2 enzyme, BCO2. So if you have a slow BCO1, you uptake more beta-carotene into your body, and then your beta-carotene is toxic to mitochondria. And so our bodies are smart, and they use BCO2 to protect the mitochondria by making apocarotenoids. And beta-apotencarotenoid, as long as there's enough retinol around to buffer it, can be good. It serves as a mitochondrial boost, helps to make energy. But if there's not enough retinol around, then you have a problem. So, okay, so anhydroretinol or beta-apotencarotenoid will cause excessive pyruvate dehydrogenase complex activity, and that leads to excessive amounts of electrons, superoxide, hydrogen peroxide, and hydroxyl radicals. And it also leads to losses of thiamine lipoate and B5, which is needed for coenzyme A. It can also cause, we recycle NAD, so I don't think you become NAD deficient, but it can kind of suck that up. And then one more, B2. So riboflavin, it could also kind of lower your riboflavin because you need it for FAD. Okay, but if you have healthy retinol in your PKC delta signalosome, then you have normal pyruvate dehydrogenase complex activity because retinol serves as a sensor. It serves as a healthy sensor inside your signalosome and helps you to make just the right amount of electrons so that you can pass them through cytochrome C. And then you also have this thing called cardiolipin that's holding your complexes in the membrane. And so you have a healthy cardiolipin. Now, If you have anhydroretinol or beta-apo-10 carotenool, and you do not have healthy normal retinol to help buffer it, and what that means is like you have lots of mitochondria in your cell, so some of the mitochondria might have anhydroretinol. That's okay. The cell can deal with that. But some of the mitochondria might have retinol, right? So that there's a balance. There's some oxidative stress maybe, but not all oxidative stress. But if you only have anhydroretinol and all your little mitochondria, there is a problem. Okay. So then you have excess hydrogen peroxide. And what that does is it binds to cardiolipin, and then cardiolipin binds to cytochrome C. And these two things bound together in the presence of hydrogen peroxide become a plasmalogenase, which breaks down plasmalogens, which normally isn't a problem because you would recycle the phosphatidylethanolamine or the phosphatidylcholine, and you could remake the plasmalogen. But if you're low in the nutrients to be able to make the plasmalogen, you just have breakdown and not rebuild. I hope that makes sense. So I think the problem is an imbalance between breaking down because of excess hydrogen peroxide, turning cardiolipin and cytochrome C into a plasmalogenase, versus not building up because of nutrient deficiencies and other factors that we're going to talk about. All right, so what happens when you break down plasmidylcholine and plasmidylethanolamine? You produce a lysolipid, and you also produce alpha hydroxyaldehydes. These are the ones that I showed you on the previous slide: MDA, ACR, HNE. HNE is macular degeneration. HNE also inhibits the TCA cycle, alpha ketoglutarate dehydrogenase. So not a good thing to have HNE. HNE can cause seizure disorder. So, okay, so you have two enzymes that can deal with these lipid peroxides. One is aldehyde dehydrogenase 7A1, and it's involved in the production of betaine. It helps to metabolize lysine, and it helps with these lipid peroxides. So there's a risk for functional B6 deficiency, and I have a whole video on that. ALDH7A1, functional B6 deficiency. Okay, so ALDH1A1 also metabolizes retinol aldehyde. So the people that I work with, they're struggling. They have a lot of vitamin A on board usually. It's just kind of building up. I think probably because of all the reactive oxygen species, it's making you struggle with NAD recycling. And so as your mitochondria stop going from NADH to NAD levels drop, and then you have a buildup of retinol aldehyde in retinol, because to get past that to retinoic acid, you require NAD. So NAD is probably too low, and so you lose your ability to use ALDH1A1, or ALDH1A1 is super tied up in retinol aldehyde metabolism. So the result is you don't have detoxified end products. The result is you have ongoing lipid peroxides. Okay. So this lysolipid will be broken down and release the phosphatidylethanolamine and phosphatidylcholine, and you'll end up with a carboxylates such as arachidonic acid, which goes to eicosanoids, which can lead to inflammation. So it's not a good cascade. It's not a pretty sight. On the labs, you could have low levels of ethanolamine or choline, or you could have normal levels. So normal levels of ethanolamine on a plasma amino acid test doesn't mean that you have no problems with your plasmalogens. It could mean that you're breaking them down, or if your ethanolamine is high, could be breaking them down. If your ethanolamine is low, it could be that you have some gut dysbiosis. We'll talk about that in a second. Okay, so let's look at how we make them, because I think the big problem is that we're breaking them down quickly because of excess reactive oxygen species. But how do you actually make a plasmalogen? Well, you have to be making DHAP. You need glucose and glycerol to do, or not both, or glucose or glycerol can become DHAP. So what can alter that? what can alter that? Well, if you have if you don't make enough glutathione, so you have a very small amount, that means you have a lot of oxidized glutathione. That's what that GSSH stands for. And if you have a lot of oxidized glutathione, then that's going to cause a high amount of dehydroascorbic acid to try to recycle that. And dehydroascorbic acid turns on the pentose phosphate shunt. So you'll be shuttling your glucose towards making NADPH instead of making DHAP, which is the precursor for making a plasmalogen. So that's one thing. If you have recurrent hypoglycemia, then you're going to be preferentially using your glucose to restore blood glucose rather than using it to make DHAP. So hypoglycemia can lower your ability to make plasmalogens. My daughter has recurrent hypoglycemia when she's not on growth hormone because she has a genetic syndrome that causes her to have low levels of growth hormone, but also her genetic syndrome causes problems in the production of glutathione. So she has a double whammy. No, I do not think she makes plasmalogens in a significant amount, and it would be explained by I like to say, I just gestured to all of you, but I love her dearly. She's wonderful. I would not trade her for anything or anyone. All right, what about lipogenesis? If you are making lipids, so if you're in a methylfolate trap and then, oh my goodness, I'll have to do a video on this. I have another new client that I actually think that his magnesium deficiency has contributed to him having hyperlipidemia. So that's interesting. So if you're in lipogenesis, then you're going to be using your glycerol to be able to make a lipid. You have to use glycerol to make a triglyceride. So then you'll have less DHAP. If you, a good thing would be is lipolysis. So breaking down fat to use it as energy, you're going to free a glycerol molecule and that can become DHAP. So exercise has been proven to improve brain health. It will help you to be able to make more plasmalogens. Okay, so once you have DHAP, then you require acetyl-CoA. Then the important thing here, I believe, is that there's an issue with coenzyme A. So coenzyme A is made with B5. But to make coenzyme A, you have to have cysteine. And I think that many people are struggling with going from homocysteine to cysteine inside the cell because that's B6 dependent. So they're struggling with actually making coenzyme A. And then also, you know, if you're making lipids, then that sucks up coenzyme A and making malonyl-CoA. So that's a problem. So that's lipogenesis. Again, a functional B6 deficiency can make it hard for you to be able to make coenzyme A. If you have excessive pyruvate dehydrogenase complex activity, you're sucking up the coenzyme A to make acetyl-CoA from pyruvate to acetyl-CoA. And then if you're in acidosis, you can actually struggle with getting cysteine into the cell. So if you're B6 deficient and you're not making cysteine from homocysteine, then you also have acidosis, then you're not getting cysteine into the cells either. And so then that can lead to low coenzyme A production. So there's multiple factors that can lead to less coenzyme A. If you don't have coenzyme A, then you're not going to be able to get to this alkyl acyl glycerol. Another component, though, is that you require a fatty acetyl-CoA. And again, CoA could be the limiting factor here, but to be able to go from fatty acetyl-CoA to a long-chain fatty alcohol that's added to the DHAP, you require NADPH. If you have a low glutathione status and lots of oxidized glutathione, then your body hopefully would choose to push the NADPH towards recycling of glutathione. If you have a B2 deficiency, though, then you might struggle in this area, and then you probably might make some more long-chain fatty alcohols, possibly. If you are making lipids, though, if you have hyperlipidemia, that's a problem, because that means that you're not going to make this long-chain fatty alcohol as much, because you're using your NADPH to build lipids. So if you have high cholesterol, high VLDL, high triglycerides, then probably you're really bad at making plasmalogens. I'm so sorry. Please forgive me for bursting the bubble. Okay. Again, if glutathione is too much oxidized glutathione, then you're going to potentially be sucking your NADPH this way. If you have a B1 deficiency, then you can't run your pentose phosphate shunt pathway, and that could cause low NADPH, and that would lower your ability to make plasmalogens. Now, if you, so let me think of it. So if you have an overactive pyruvate dehydrogenase complex because of anhydroretinol, then you probably also have a B1 deficiency. And then when you supplement with B1, if you have a paradoxical effect, like I said before, might be because you're turning back on your anhydroretinol PKC delta signalosome. And maybe that's the reason why people have so many struggles with high dose thiamine. Yeah. And one of the side effects of having an overactive pyruvate dehydrogenase complex is hypoglycemia, because you're just going through from glucose to pyruvate really fast. And that's one of the paradoxical effects, I believe, of high dose thiamine. All right, moving on. All right, so once you've made this alkyl acylglycerol, then you need CDP choline or CDP ethanolamine to make plasminylcholine and plasminylethanolamine. Sorry, see, I said the E. All right. So this first step, again, it happens in the peroxisome. That's where it happens. So now we're going to move on. We're going to look at what happens in the endoplasmic reticulum. All right. So first, we're going to focus on ethanolamine. So ethanolamine, where do we get it from? We get it from our diet. So that would be like eggs, seeds, we could say supplements, dairy and fish and meat. Those are all good sources of ethanolamine. We could also take a phosphatidylethylamine supplement. Sunflower lecithin is really high in well, not really, but it's high in phosphatidylethylamine. You can actually get your ethanolamine from phosphatidylethylamine that's inside of your body. And this would not be the way you would want to harvest your ethanolamine, because phosphatidylethylamine is a component of cardiolipin and phosphatidylinositol. So really, you want your free ethanolamine, if possible, to come from other pathways or from your diet. To be able to get ethanolamine out of phosphatidylethylamine, it requires serine. So that's something to think about as well. So what could lower your ethanolamine levels? Well, Candida or other fungus or other bacteria in the gut actually can eat ethanolamine. And yeah, I actually have some slides. So I'm trying to do this like easier part now, but then I'll just go through like what I went through from a research standpoint, and I'll talk a little bit more about that. So, serine deficiency, if your serine levels, like if you're not going from glycine to serine because you have a B6 issue and your serine levels are low, well, that's going to make it hard for you to recycle the ethanolamine in your body as well. Okay, so what could cause problems with serine, and that kind of addresses also this pathway over here where you go from phosphatidylcholine to phosphatidylserine and you produce choline, okay? So what could actually cause a problem with that? Well, if you have very high pyruvate levels, because let's say that overactive PDHC results in the thiamine deficiency, and then you're stuck at pyruvate, and you just go from glucose to pyruvate over and over again. And then pyruvate gets shuttled around. If you have high pyruvate levels, it will complex with serine to form hydroxypyruvate, and I'll show that in a bit. And I believe that that's a cause of hyperoxaluria. I think that a block in pyruvate dehydrogenase complex after the depletion of all these micronutrients leads to hyperoxaluria. All right, so again, you could, if you have a B1 lipoate or B5 deficiency, that could lead to high pyruvate levels in the setting of a normal diet with carbohydrates. Okay, so you can see that you have to harvest the ethanolamine, or you have to make it in your body, and we'll talk about that in a minute. And then choline. Choline is, again, same type of thing, and it's in supplements. You can get it from your serine glycine metabolism that I'll show in a minute, and then also you can get it from your cell membranes. So choline, phosphatidylcholine, is a major component of cell membranes. It's also what you use to make VLDL. Okay, so if you're making a lot of VLDL, lots of blood lipids, maybe because you're in a methylfolate trap, maybe because you have low magnet levels, resulting in lots of lipids being made, then you're going to struggle with the amount of phosphatidylcholine available to make cell membranes. But you can harvest choline to be able to make a plasmalogen by using serine. It's called a base exchange. So serine takes the place of choline, and you get phosphatidylserine, and then the choline can be used to make plasmalogen. So before I go on to down here a bit, before I go on, I want to talk about the serine glycine metabolism. So if you don't eat choline, you won't immediately die from choline and ethanolamine deficiency. Do I like eggs? Yes, I do. I think they have benefits. Do I think that they backfire for people? Yes, I think they do. And I at first thought it was a sensitivity to vitamin A, like anhydroretinol maybe is being made by them. But I honestly think that people who do badly with eggs, the real thing that's going on is, or any sort of choline supplement, or choline source, is I think that they have a pathogenic bacteria in their gut, or Candida, and I think it's feeding those, and then those are producing alcohol, and then that's making anhydroretinol, and that's the bad feeling that you get. You feel like sick, brain fog after eating an egg. Dude, totally bacteria eating up the egg and using the ethanolamine and the choline for their own benefit and leaving you starved of it. Okay, but if you don't eat these, you can perform the choline cycle. If you have B2, B6, NAD, SAM, acetyl methionine, and low lipid peroxides and low hydrogen peroxide levels, then you can make your own ethanolamine and choline. Okay, so let's go through what that looks like. So what it looks like is you would be able to go from glycine, and by the way, glycine and serine, they go back and forth. Okay, so you can go from glycine to serine using P5P and serine, serine hydroxymethyltransferase. Yeah, hydroxy? Yeah, hydroxy. So, so going from glycine to serine, and then from serine, so to go from serine to ethanolamine, it requires P5P. So using serine decarboxylase, and that would make ethanolamine. Then you require SAM. It's actually 3 rounds of acetyl is needed to be able to make ethanolamine. You can see the methyl groups added. So, so here's ethanolamine, and it has just these 2 CH2s here. And then you're going to add methyl groups, which is CH3, and you see 1, 2, 3. So you have to have 3 rounds of SAM to use up a lot of methionine. If you're a vegan, to lose a lot of your methionine to be able to make ethanolamine in your body. Not that you can't get some from seeds and stuff, but maybe it's not enough. Yeah. Okay. So then you make choline. And then choline requires B2 in the form of FAD to be able to become betaine aldehyde. And then betaine aldehyde requires ALDH7A1 to be able to become betaine or betaine trimethylglycine. Okay. And betaine trimethylglycine will perform this betaine homocysteine methyltransferase reaction, and it's a backup for making methionine. Okay, so in our liver, in our kidneys, and some parts of the brain, they think that this happens, especially in an MS model. We use BHMT to be able to go from homocysteine to methionine. So if you don't consume betaine, then you have to make it. Okay, and you'll make it from ethanolamine or choline. And if you don't have very much ethanolamine or choline, so say you're struggling with B6 levels, then you'll break down your lipid membranes to be able to harvest that so that you can make enough betaine to run BHMT methylation. And when you're on oxidative stress, high nitric oxide or high hydrogen peroxide levels, your body preferentially uses betaine to run methylation. So there's a big issue here. Okay, remember that ALDH7A1, this inset right here, it shows lysine metabolism. If you're busy with ALDH7A1, dealing with lipid peroxides or dealing with making betaine, then you're not metabolizing AASA, that becomes P6C, that binds to your P5P, it makes it inactive, and then you can no longer go from glycine to serine. You're no longer being able to make a sufficient amount of your own ethanolamine. So after you've made this betaine, it goes to dimethylglycine, then to sarcosine, and then back to glycine. If you have high sarcosine levels on your plasma amino acid test, that's a classic sign of a B2 deficiency. Me. I'm just sharing with you, it happened to me. The problem with that is, even though it hasn't been shown in literature, it has been shown in like outside the body that sarcosine can actually chelate copper, and then that could cause a functional copper deficiency. And that leads to problems with dopamine beta hydroxylase. It leads to problems with deactivating histamine. It leads to problems with, there's one more, making white blood cells. So yeah, lots of stuff there. B2 is important. Okay. I think I'm done with this slide. Oh, no, I'm not. So one thing to know is that when you're in a high hydrogen peroxide state, so say your copper is low, your zinc is low, you don't have really good, actually that wouldn't be that if your selenium is low, and you're struggling with glutathione peroxidase, then you may end up with an inhibition in MAT, which is what helps you to go from methionine to acetyl methionine. So that would be bad. That would mean that you're struggling with making ethanolamine into choline, and it could, if your P5P is okay, you could end up with like higher levels of ethanolamine on your plasma amino acid test. So, okay. Now let's get back into this pathway. So if we have, actually I'm going to go backwards because I want to show you this. So if you have low SAM levels, let's say that hydrogen peroxide is inhibiting your methionine to SAM, or let's just say that you're struggling with methylation. Maybe you're sucking all of your methyl groups to high histamine. You have a lot of histamine, you're trying to break it down. So you're using up your SAM for that. If you have a B12 or folate deficiency, you're probably going to struggle with making SAM, especially in the rest of your body, because you only use B12 or folate to run methylation in the rest of your body, outside of the kidneys, liver, and that small part of brain that they think may be doing it. And A high arsenic diet will deplete your SAM. So, and then MAT inhibitors will also lower SAM. So boswellic acid, a lot of people resort to this as an anti-inflammatory. It's boswellia. They resort to it as an anti-inflammatory because there's a lot of inflammation as you start to break down your plasmalogens. You make a lot of eicosanoids. And so, ow, 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 I'm going to use something natural to help me with my pain. Raising my hand here. And then that actually inhibits your ability to make SAM. And then that can lead to improper recycling of these phosphatidyl versions of choline, serine, and ethynylamine. So if you can't run this reaction, it's PEMT. If you can't run PEMT, you can't go from phosphatidyl ethynylamine to phosphatidyl choline, and then you will have low phosphatidyl serine levels just because you're sort of getting stuck. I mean, you can go from phosphatidyl ethynylamine to phosphatidyl serine. You can do this as well, depending on if you're doing a good job with serine metabolism too. But having very low phosphatidyl serine levels is a sign of early sign of apoptosis. And in actuality, what happens is the cell will actually flag using serine. So it moves serine to the outside of the cell, and it becomes a flag for the cell to be catabolized basically and eaten up. Pretty crazy, right? Okay. So that's a possibility as well. So something to know is that this enzyme PEMT, so whenever there's a methylfolate trap and methylfolate is stuck, it turns off the enzyme GNMT, and that's in video number 3, and it turns on PEMT, and then that will lead to lipogenesis. And then in that process of making lipids, it actually steals phosphatidylcholine. And so phosphatidylcholine can be depleted by lipogenesis, and then it can also be depleted when you have a betaine deficiency, because you're going to use your PC to break down, you use choline to make betaine. Okay, go past this. All right, so now we're going to talk about the next step. So let's say that we're finally making ethynylamine and choline. Well, the next step is to use this enzyme PCYT2, okay? And this particular enzyme is what makes the CDP choline, the CDP ethynylamine. So the PCYT2 is decreased by insulin resistance. So if you have insulin resistance, you're not making many plasmalogens. What can cause insulin resistance? Acidosis can, obesity can, a high triglyceride to HDL ratio greater than 3 in adults and greater than 2.27 in kids is indicative of insulin resistance. Chromium deficiency, I don't have it listed here, but if you're chromium deficient, you're going to be struggling with insulin resistance as well. And I think that chromium gets depleted from toxic anhydroretinol because you're pushing pyruvate glucose to pyruvate so quickly. I think that you end up having to uptake more glucose. Okay, so there's different phases of the anhydroretinol toxicity. In the early phase, because you're turning on energy production so fast in one set of mitochondria, then you're going to end up having to use chromium in glucose uptake. And that's funny because I had hypoglycemia as a kid. Goodness. All right. So, okay. So how do we increase it though? Well, it's increased by thiamine sufficiency. So, having enough thiamine can help your PCYT2 enzyme work, and that's a good thing. But the high dose thiamine transporter, OCT1, if you go very high dose on thiamine, it causes fatty liver. And if you're making lipids, remember you're using up your phosphatidylcholine. So there's a sweet spot, I think, for thiamine. And I shared in the previous video that I have fatty liver disease, and maybe it was because I did high dose thiamine. I mean, not to like blacklist it, but I think that there's a lot of Goldilocks nutrients, and we're just now discovering it. So I'm not saying, stop your supplement, talk with your own healthcare provider about it, maybe get an ultrasound, see if you have fatty liver, and then think about the OCT1 transporter and how metformin works to lower fatty liver disease is it causes thiamine deficiency. So, and it actually results in less lipid production in the liver. You got to wonder if this is all just interrelated though, right? Okay. All right. So let's see. Was there anything else I want to say? I think that's it. So what do we need to do, right? That's a big question. But so here's my giant map all worked out. Okay. So here's the solutions. I think treating gut dysbiosis, I really didn't want to have to say this because goodness gracious, what a job to try to treat gut dysbiosis. Our world is full of glyphosates. It's in our water supply. We have so many toxins that mess with our gut. So I've been researching KPV peptides. One of my friends, Daniela, sent me a message about it, and my mind was blown. I love when people share things with me. Please keep sharing. So I think that people are struggling with making alpha MSH, which is a KPV peptide is actually the functional group of alpha MSH. And I think it could be low because there's a lot of stress that happens when you're in toxicity. And so potentially you have a high cortisol state, which would decrease the release of ACTH, adrenal corticotropin hormone. And adrenal corticotropin hormone is when a side offshoot of it is alpha MSH. And one of the enzymes is NAT, and that's actually the last enzyme in producing alpha MSH. And it says H2O. It's actually hydrogen peroxide, not H2O. Hydrogen peroxide inhibits NAT, which is the very last enzyme. And so I think people are struggling when they're in oxidative stress to be able to make alpha MSH. And that's leading to low antimicrobial, or it's leading to gut dysbiosis because alpha MSH is an antimicrobial, a natural antimicrobial that we make in our body. So I do think KPV peptides make sense. I do. I actually ordered some for my own family, and I'm going to give them a try out, and I'll report back on it. All right, so grapefruit seed extract. So grapefruit seed extract kills Candida. I'm not sure if it kills other fungal infections. It has been shown to produce a favorable gut profile. Some people believe that it's tainted with triclosan, so that's a problem. It also is a CYP3A4 inhibitor, which means it could cause problems with bile flow. In my own clients, I tell them if they're taking grapefruit seed extract and then they have gallbladder pain greater than 3 days, then there's a problem and they're very sensitive to that particular treatment for gut dysbiosis. Nystatin, it only treats superficial Candida. I don't recommend it. I made that mistake with one of my kids when they were very young, and I think that it just contributed to the Candida going deeper into the tissues. Diflucan, it treats systemic Candida, but it does have toxicity issues. It's really hard on kidneys. So if you already have underlying kidney disorder, probably diflucan is not the best choice. Uva ursi, it's not for children. I didn't research it because it's not for children. So sorry. Okay, lactoferrin, you could use that to help. It's an antimicrobial as well, but you have to be careful long-term because lactoferrin can bind to iron, which might not be a bad thing if you have iron overload. But iron is needed for CYP enzymes. You need it for working with conatase, alpha-ketoglutarate dehydrogenase. So we need iron. But also lactoferrin can bind to copper, zinc, and manganese needed for SOD. So it's long-term, it's not your best choice. It's not. I really think KPV peptides are going to be the winner here. You want to avoid low carb diets because fungus will infiltrate deeper into the epithelial tissues to access your blood glucose. So eating low carb is not the best way to treat Candida. It's kind of been disproven. Why do I think treating gut dysbiosis is so important? Well, obviously, I think that gut dysbiosis contributes to anhydroretinol production, but also these pathogens eat your ethanolamine and your choline and your serine, and we don't want that. We want those to be taken up into the body to decrease the burden on using the choline cycle, because B6 is a problem here. I think among the people in our group, B6 is a huge thing, where we're all like, high glutamate, low GABA. Oh, and by the way, glutamate won't usually show up high on a plasma amino acid test because our bodies are smart and our bodies know that glutamate is toxic. And so the body will turn it into glutamine, but then high glutamine levels can serve as the substrate to make glutamate in the brain. So just because your glutamate's normal in your lab doesn't mean that you're in the best shape ever. Okay, so we want to discourage lipid peroxides. So the first step is always restore your minerals. Make sure that you have normal zinc, copper, selenium, and manganese. I have a question mark against manganese because in the US, there's some water sources that are toxic in manganese. So it's something that you should maybe consider that you may have plenty of it. A lot of people do hair analysis to check that. So you also want to consider your pH, because either consider using some bicarbonate under supervision of your own healthcare provider or follow an alkali diet, because if your pH is acidic, you're going to struggle with making glutathione. Also, you're going to struggle with making plasmalogens because an acidic pH causes insulin resistance. And remember, a plasmalogen is your brick wall. It does a good job soaking up lipid peroxides. And normally then it's broken down by the plasmalogenase. And then normally it's rebuilt. We take the constituents of it and make a new one. Interestingly, the half-life of a plasmalogen, and I believe it's the choline version, is 30 minutes. And then the ethanolamine version is 6 hours. So this is something that's happening quickly. It's not something that's taking days or months to do. So we can make a significant change in our plasmalogen levels within the course of the day. And you can go from feeling like a crab to feeling better. It's pretty neat, right? Or the opposite. You could be feeling good and then something happens and then you feel like crap. So in theory, at least that's what people are telling me. Like, they're like, I ate this and then I felt so bad. Makes sense, right? Our bodies, it's a minute by minute instead of hours. Okay. Or even days. You can use B12 to mop up nitrogen oxide, because nitrogen oxide is one of the inhibitors of methionine synthase, along with hydrogen peroxide can also cause this problem. And the inhibiting methionine synthase can cause that functional B6 deficiency through the ALDH7A1 issue. And then you would have low GABA levels. If you have low GABA levels, then you're not able to upregulate all of the enzymes that help you to get rid of oxidative stress. Always restore your minerals before you restore betaine, because betaine will restore the function, like the function of B6, and that will upregulate GABA. And if you upregulate GABA and you don't have enough zinc, copper, selenium, and manganese, then you're in trouble. I only know this because I made the mistake. So I went downhill really fast. My brain was not functioning. It was horrible. And I was like, I can't lose my brain, but it's okay. My backup career is homesteading. So if I actually lose my brain, I'll just go out there and have to have a bunch of sticky notes on everything to remember what I'm supposed to do in the garden. And that sounds like a joke. I know that some of you are really struggling, and I was there. So my heart goes out to you. Yeah, it was horrible. I cannot imagine. But you can heal. If I can get better, you can get better. I used to have like the MS cold water sensation. And this really, like, I had Procera sign. It's a little bit there where I was doing this, like this shocked look. It was horrible. I was so scared for my life. Okay. All right. Vitamin E. By the way, I believe in the hope of like I have a Christian hope, so I was scared for this life in my family, but after that, I was like, okay. All right, vitamin E and coenzyme Q10. So vitamin E helps to mop up the oxidative stress lipid. It actually deals with the hydroxyl radical that causes the lipid radicals. It causes the propagation and worsening like domino effect. Coenzyme Q10 will deal with the excess electrons. It also can help with recycling of vitamin E, and I'll show you that in a second. Oh, actually, I'm going to show it to you now. Actually, it's not on this slide. It's on another one. This is from the Linus Pauling Institute, though, and it shows you the role of each of these like antioxidant components in dealing with a lipid peroxide. Okay, so this is the lipid peroxide, and you use vitamin E, and then vitamin E is recycled by vitamin C, and then vitamin C is recycled by glutathione, and glutathione requires NADPH. So these all kind of work together. So the question is like, what about vitamin C? Well, high-dose vitamin C becomes hydrogen peroxide. I'm just telling you right straightforward. It degrades to hydrogen peroxide. Also, vitamin C can become oxalate in the body. So do you really want to have massive amounts of vitamin C at one time? No. Slow release, time release vitamin C would work better, and keeping the dose low, like maybe 250 milligrams a day. Some people can tolerate 500 milligrams, but it's a Goldilocks nutrient. We don't want to go crazy with vitamin C. It can cause oxidative stress. The vitamin E, I would be, well, let's say CoQ10. Some people end up with insomnia from CoQ10, so that's just something to realize. I haven't experienced that. By adding more CoQ10 didn't make my waking up at 3 a.m. any worse. Kind of think I wake up at 3 a.m. to be alone, right? So I make videos. But vitamin E, here's something, there's like a little paradoxical reaction here with vitamin E that happened to one of my clients. So they were on 40 milligrams of vitamin E. They upped it to 80 milligrams, which is about like I think it's around 125 IUs. So not very large dose. And then developed milk alkali syndrome. And it's because they had been deficient in vitamin E. And then when they got repleted in using the vitamin E with all of their, to mop up all the oxidative stress, there was extra vitamin E available finally when we upped the dose. And that helped with making, going from 25 OH vitamin D to 125 OH vitamin D. That caused an uptake of calcium from the kidneys and calcium from the calcium from the intestines, and maybe potentially even dropping calcium from the bones, because this person already has high vitamin A. So they have lots of osteoclast activity, lots of calcium coming from the bones. So altogether, blood calcium levels went up. And when the blood calcium levels go up, then bicarbonate also the bicarbonate didn't go down. Yeah, the bicarbonate went up too. And so overall, it was horrible for this person. They were just screaming and like it was like psychosis. So if you have a paradoxical reaction to vitamin E, it might be that you just went too high on it. Then I would back off, especially if you're doing vitamin E and bicarbonate, and then you start to feel crazy in the brain, you can't think. It's the combo of that. You're probably getting milk alkali syndrome, very like alkalosis. So be careful with that. And it could be, this is an interesting thought, it could be that the individuals who are struggling with low bicarbs and acidosis, it's actually vitamin E deficiency. Okay, it could be that. And so what if just making sure that you get enough vitamin E in solves the bicarbonate problem? That would be a really cool thing to look at. Okay. So should you use a glutathione patch or transdermal? That might be an option. Oral glutathione is problematic because yeast love glutathione to help them be stable. I mean, liposomal glutathione may or may not get past the Candida. I would just be careful with that. Could you do NAC? You could, but some species of Candida have adapted to eating cysteine. I think that's actually the reason why NAC helps to break down biofilms, is because Candida, when they're eating, break down their biofilms. And so potentially that's how NAC is working. I'm not 100% sure on that. That's just my brain thinking. So what I have done with my own children who have Candida is, when I'm treating Candida, I'll use NAC for the first couple of, like, at least a week of the treatment, and then I'll back off on the NAC, and so that, you know, they're not feeding it. I feel like it's a delicate balance. Okay. I would avoid high testosterone levels. Sorry, guys, or testosterone injections, like anything like that. Just like high testosterone inhibits the CBS enzyme. And so then you're struggling with making glutathione. You'll also struggle with making coenzyme A, because if you can't get cysteine, if you're not making cysteine in the cell, then you can't make coenzyme A. So not a good idea. Okay. All right, so avoid seed oils. I'm going to go on to this next slide here and look at alpha lipoic acid. So alpha lipoic acid is not for anybody who has mercury toxicity, says my mercury toxic friends, who are very helpful to me. They say that it tends to just move the mercury around in the body and doesn't really help you to get rid of it. So they think that it could actually make people more sick, because the mercury comes out of storage and then is like inside the cells wreaking havoc. For example, it can cause pyrrole disorder, because mercury can inhibit some of the enzymes in the porphyrin pathway. So it can make you make bad heme. So caution for anybody who has mercury toxicity. If you don't have mercury, like if you've been confirmed to like not be high in mercury, then alpha lipoic acid can act as an antioxidant. And this is where the coenzyme Q10 comes in. So what happens here is you might have a lipid peroxide, and to stop the propagation, your body uses the alpha tocopherol, and it becomes an alpha tocopherol radical. Then it's recycled by one of these three nutrients. So coenzyme Q10, right? That's neat, because you can supplement with this. You know, ask your doc or your healthcare provider about it. Vitamin C, remember, vitamin C is Goldilocks. Too much becomes hydrogen peroxide or oxalate. And then glutathione. So if you are struggling with making glutathione, coenzyme Q10 could be helpful. And then also alpha lipoic acid, or lipoic acid. Here's a thought though. What if that's a major problem in the body? What if lipoic acid becomes a sort of backup pathway and it's sucking up all that, or dealing with oxidative stress? Something to know about when you take lipoic acid, the Linus Pauling Institute says that you actually don't incorporate it into enzymes. It can only act as an antioxidant. You have to be making lipoate in your own body. So there's a process for that. Maybe I'll go over it in another video. So yeah, so that's important. And then then you of course would need NADPH to be able to recycle this lipoic acid. So there's that. So what about increasing PCY2 activity? Well, acidosis causes insulin resistance and decreases PCY2. So if you improve your pH, that would help. So you could check your anion gap. So one of the difficulties that I find is in my clients is that they get their labs back and they're told that they're normal, which, I mean, they are if nothing's out of range. But that doesn't tell you if you're in acidosis or not. You need to go and calculate your anion gap, and sometimes it's on your lab, but it doesn't tell you like what kind of acidosis you're in. And there's actually a calculator called ND-Calc, and I'll put a link in the description. And you can go online and you can put in like your sodium, your chloride, your CO2 levels. In other countries, it's called your bicarb levels. And you can put in your albumin if you want. We usually only use albumin to adjust the anion gap if the albumin is like super off. But And then you can look at the results and you can determine what type of acidosis you're in. I mean, you could just be in ketoacidosis, but you could be in like a renal tubular acidosis, and that's very much bicarbonate. But either way, when we see acidosis in a clinical setting, we usually treat with some type of bicarbonate, but under supervision of a physician. So my most sick client, she is able to get serial labs done, so she can get her labs checked whenever she needs to, and then we can adjust the bicarbonate. So if you're struggling with taking bicarbonate and you feel really bad, sometimes it's probably because you're going too hard on it, like you're causing metabolic alkalosis. All right, so another thing that you could do is exercise 3 hours after a meal, and that would help you to burn your triglycerides. And also that would provide glycerol, because glycerol will come out. It can like come out of the muscle and then it can be sent to the liver. And then, yeah, you can use it to make your plasmalogen. If you're doing a ketogenic diet, don't exceed your caloric needs, okay? Because you don't want to end up having to store fat. A ketogenic diet, you're going to be breaking down fat, freeing glycerol, but you don't want to be sucking up the glycerol and making lipids. So a ketogenic diet is not a free-for-all to eat as much food as you want. It's just not. So and that's mostly how people use it. They use it as a free-for-all diet. Well, I can eat as much calories as I want because I'm on a ketogenic diet and I won't gain weight. Well, you can stop making plasmalogens. That wouldn't be good. Sorry, that was really sarcastic. I've just dealt with ketogenic diets a bit, and I'm not mad at the ketogenic diet. I just think that caloric control is also important if you want to save your brain and all the other cell membranes. All right. Yeah, because a ketogenic diet, it can also increase the risk of low DHAP. So that's important to realize. Like you really need so let me think about it, because you're using like your glycerol backbone to potentially help to restore glucose. It's going like backwards. Okay, so you can do gluconeogenesis with oxaloacetate, which comes from aspartate or asparagine. You can actually make gluconeogenesis happen that way, but you can actually use your glycerol backbone to produce glucose instead of DHAP. Okay, what about thiamine? Thiamine increases PCYT2, but how much thiamine is appropriate? Because it does upregulate the activity, but I think it's probably a normal thiamine status that helps with that, not necessarily high dose, because high dose thiamine interacts with OCT1 transporter and it causes fatty liver disease. If you're making triglycerides, then you're using your glycerol for the triglyceride, or if you're making diglycerides, you're still using glycerol backbone for that process. And if you don't have glycerol, you're not making DHAP. All right, so here's another solution. You want to increase your intakes of phosphatidylcholine, phosphatidylethanolamine, or phosphatidylserine, and that would help spare some of those things in your lipid membranes. But if you have a reaction to it, then you probably have Candida. So if you have low ethanolamine levels on your plasma amino acid test, it is quite possible that you have gut dysbiosis and that the bacteria are consuming your ethanolamine. Or not just bacteria, it could also be fungus, so Candida, aspergillus, stuff like that. You might consider phosphatidylserine, because like, especially if you have fatty liver disease, because it's been shown to help with fatty liver disease. But it might be like you yourself could digest the phosphatidylserine into just serine. Like you could break off the phosphatidyl part and just have serine, and then that could actually be the Candida's candidate pathway too. All right. You could try betaine to spare phosphatidylcholine, but again, after you restore your minerals, or you'll be like me and almost have no brain. Or if you are suffering with that, my heart goes out to you. I seriously understand. It's like very hard. It's painful. All right, endogenous oxalate producers, maybe temporarily lower your carbs, because I believe that people who are stuck with this, with hyperoxaluria, and it looks like primary hyperoxaluria, but it's not, because they don't have the genetic capacity for that. I believe that that's because of anhydroretinol and depletion of all of the cofactors, and then there's a buildup of pyruvate. So going low carb would actually result in sparing, hopefully sparing of serine. And I can actually, I'm going to do a video about that hyperoxaluria thing. I would also avoid prolonged low carb diets because if you're not good at burning fat, so let's say you're on a low carb diet, but you're not very active. Well, you're not freeing glycerol, and then also you don't have much glucose, right, to be able to make DHAP, which is needed to start the plasmalogen formation. And you want to avoid the methylfolate trap, because that would harvest phosphatidyl. So that would harvest phosphatidylethanolamine in that PEMT reaction to make phosphatidylcholine, and then that could actually ruin your ethanolamine levels in your plasma membranes. And remember, that's the one that's needed for cardiolipin, and cardiolipin holds all your complexes in place. We need cardiolipin. So you might try reducing nitric oxide inducers. So stay away from like celery and high nitrate foods, beets, those things all induce nitric oxide. It's a Goldilocks nutrient, so I have a video on that. It's not that all nitric oxide is bad, it's just we need a certain amount in our body. All right, one other solution is going crazy expensive. If you got the cash, you could try plasmalogen supplements. So what plasmalogen supplements are is they harvest the plasmalogens from things like oysters, and I can't remember all the stuff. You can go to the website and look. And then they make a supplement. And when you take the supplement, your gut lipase actually sort of activates it, and then it's absorbed and it enters in at the 1-alkyl 2-DHA-OA glycerol molecule. And then CDP ethanolamine is the only thing that you would need to be able to make your plasmalogens. But then also you can actually, the plasmalogens are in the supplement too. So you can go to this prodrome.com, and I got this diagram off of Dr. Goodeno's. I don't know him, but he has a good diagram, so I referenced it. So you can go to his website and see what he's all about. I can't vouch for his practitioner status, but the fact that he's talking about plasmalogens is pretty good. All right. So would you like to know more? This has been a really long video, but my brain's still working, so I'm just going to keep going. But if you don't want to know more, you can stop there. So here is a slide showing all the unique functions of this is, by the way, how I started out taking notes, basically. So these are the unique functions of the S-vinyl ether bond and the SN2 polyunsaturated fatty acid, okay? The function of these plasmalogens is because of this special vinyl ether bond. So one thing that they do is they reduce the phospholipid surface tension and viscosity in lipid membranes. So that's good. It gives you fluidity, and a fluid membrane works better than a stiff membrane, right? To a certain extent. I mean, we don't want like extra fluidity, but again, everything's about balance. It's involved in synaptic transmission. You need it to make alveolar surfactants. So this is would be related to asthma, right? Also, this surfactants help you to be able to exchange oxygen. It's something that after they actually give steroids during pregnancy to help the alveolar surfactants develop if a baby has to be born premature. I'm not sure exactly how the steroids help with that, but it's needed for proper signal transduction. You need it for membrane vesicle formation that I already talked about, like VMAT or MAT. It alters the ion transport. So if you're struggling with like different versions of supplements, like say like all the chloride versions of supplements are causing you problems. Maybe it's because you're struggling with your transport of like sodium, potassium, and stuff like that. Chloride ion, right? After it alters platelet activation factor. Again, it plays, I've said this before, it plays a role in the regulation of fusion, fission, and fluidity of the cell membrane, control of membrane proteins, protein activities. So if you, in diabetes, what if it's just plasmalogen issues? What if the membrane is struggling, right? And so the cell signaling is off, and it acts as a reservoir for secondary lipid messengers too. So here are some labs from different clients. This first one is actually Zoe. She's always had low ethanolamine, pretty much her whole life. So I believe that this is gut dysbiosis. And here's another one of my clients, and the lab here makes it look like it's really normal to have an ethanolamine of 5, but it's not. Anything that's low like this means that there's probably some type of gut dysbiosis going on. And then over here, this is another client, and you can see like they look like they have great ethanolamine. That's perfect. It's beautiful. Ethanolamine is green, phosphoethanolamine is green, phosphoserine is in a good place. But then if you look up here at their lipid peroxides, they're off the chart. So really what's going on is there's a lot of I'm struggling because I'm getting tired. Plasmalogenase are sky high because of excess hydrogen peroxide. That's leading to the blood levels of ethanolamine and phosphoethanolamine. All these things are starting to look normal because they're being broken down out of the lipid membranes. So normal doesn't always mean good. You have to look at the whole picture. You can see the glutathione is super low. The coenzyme Q10 is high on this lab. Probably, I think it's because there's like there's a block in the pathway so that more coenzyme Q10 is being made. I can't remember if they supplement or not, though. That's another possibility. Okay. So this is the original chart that I was making to talk about plasmalogens. And you can see it's like a little less like eye friendly, maybe. I don't know. But I wanted to talk about regulation of plasmalogens. So normally there's a regulatory effect where inside, let's see, there's a signaling monitoring that happens that it's related to FAR1. So the stability of FAR1 is regulated, and that controls whether you start making plasmalogens or not. But this is also NADPH dependent, this FAR1. So again, if you are struggling with NADPH, then you're going to be struggling with plasmalogen formation. But basically, there is a sensing mechanism that would help you to be able to upregulate plasmalogen levels when they're required. I just think that there's some broken pathways downstream. So here's a little bit more in depth about making them. Remember, you start with DHAP in the peroxisome, and you have the long chain fatty acyl-CoA, and it comes down here, and then you add the ethanolamine or the choline, and then you get choline or ethanolamine, glycerophospholipids, and then there's a desaturase, and then you have the plasmalogen. So where does this DHAP come from? Here's DHAP. It can come from glycerol. There's like an intermediary product, Growth3P, which is kind of interesting to read about. So the link, I'll try to put a link in the notes. But you have glycerol as a source of DHAP or glucose as a source of DHAP. So before overactive pyruvate dehydrogenase complex causes thiamine deficiency, high glucose, there's a high glucose influx. There's high glucose influx, but there's a decrease in DHAP because this pathway is being pushed forward. So you're going from glucose to pyruvate, and then, it's kind of being shuttled faster. It's possible that DHAP goes low, but then there's increased reactive oxygen species and increased nitric oxide, and then that causes a methylfolate trap from all of that happening, and then that could steal glycerol from making for lipogenesis. So there's a lot of ways to be broken here. So not a lot, but a few. So you can have problems with your glycerol. And I kind of went over that again earlier. Oh, I was showing you. Okay, so what about the ketogenic diet? Well, ketogenic diet produces acetoacetate, beta-hydroxybutyrate, and acetone. Okay, so here's acetone, and acetone is dealt with, you either breathe it off or you metabolize it. So if you have a large amount of acetone, there's only so much that you can get rid of through your breath. And so the metabolism makes hydroxyacetone. And then you use your NADPH. Again, that's not good because you need to recycle glutathione, so it puts a stress on that. Use your NADPH, and you eventually will make methyl glyoxal. So let's look at that, methyl glyoxal. So here's methyl glyoxal. It comes from acetone, and methyl glyoxal requires, to be able to be detoxified, it requires glutathione. Now, it should also recycle glutathione, okay? So glutathione should be recycled, but overall, this is a burden, a huge burden on your glutathione levels in your body if you're in ketosis. It's not a good situation to be on a ketogenic diet if you're struggling with oxidative stress, or you're struggling with making glutathione. So if your glutathione levels are being sucked into dealing with acetone becoming methyl glyoxal, then you're going to overall have less glutathione that is reduced. You're going to have more glutathione that's oxidized because there's less overall glutathione available. That means that you're going to have to activate the pentose phosphate shunt to be able to keep recycling whatever little glutathione you have left that's available that's not dealing with methyl glyoxal. If you activate the pentose phosphate shunt, then your glucose is being shuttled this direction and you're not making DHAP. So chronic ketogenic diet, I really do think it's not good for plasmalogens. So how could that be fixed in a ketogenic diet? It could be by exercise, because if you're exercising, then you're going to have more glycerol, which would come in at glycerol aldehyde 3P. If you are on a ketogenic diet, exercise could provide you with the DHAP that you need. Because again, you're going to be struggling. You're causing this cascade of using up glutathione, and then requiring more NADPH, which means less glucose is coming down this way. More is going through the pentose phosphate shunt pathway. And then on top of that, you have to make sure that you are pretty sufficient in making coenzyme A. Okay, so that's important because if without the CoA, you're not going to make a plasmalogen. So B5 is important here, pantothenic acid. Just a side note, biotin and pantothenic acid compete for absorption. So if you're on a B complex vitamin, which one are you getting? Are you getting the biotin or are you getting the pantothenic acid? Also, lipoate competes. So those three things, pantothenic acid, biotin, lipoate. If they're all in your B complex, are you even getting any benefits? That's a big question. All right. Let's see. So acetone can increase the burden on glutathione. And if total available glutathione goes down, then more oxidized glutathione is produced from the remaining glutathione, and that increases glucose to the pentose phosphate shunt pathway. And then that lowers glucose shuttling towards DHAP. Okay, so if you're on a ketogenic diet, you probably need to increase your activity level so that you get more glycerol, especially if you're on a ketogenic diet, but you still have high lipid levels. That's a problem. That's not a good thing. So what about the coenzyme A? What about it? We have to make it, okay? We make it in our body. We use pantothenic acid, but this second step here requires cysteine. So if you are struggling with B6 and you're not making cysteine from homocysteine, then you're not going to be making much coenzyme A. It's going to be a problem for you. If you're in acidosis, then it's going to be harder for you to bypass the need to make cysteine because acidosis prevents the uptake of cysteine from the blood. So this is a big issue. Pantethine, a special form of pantothenic acid, can help restore coenzyme Q10. So something I've figured out, hindsight, is that you need to restore betaine before you start taking pantothenic acid. And I'll show that in the next slide. Okay, so because it helps with glycine metabolism, and then that becomes a big problem. Okay, so if you start taking pantothenic acid and you actually have a low betaine diet, you may get worse, like very badly worse with a functional B6 deficiency. So, and I will actually show that. So let me go here. So here, if you start taking pantethine, or if you start taking pantothenic acid and you actually happen to be able to make some coenzyme A from pantothenic acid because there's just enough cysteine around to be able to do it. Well, that actually upregulates the lysine metabolism pathway. So you would go, you would use your coenzyme A to help metabolize the lysine. So then lysine goes to sarcopene, and then sarcopene goes to alpha amino adipate semialdehyde, or AASA, and then ALDH7A1 is needed to convert that to AAA, and that becomes acetyl-CoA. Well, the problem here is that now if you get your coenzyme A back on board before you fix your betaine issue, because remember, you're stuck in BHMT because of oxidative stress, and you're making betaine with ALDH7A1. If you replenish your ability to make coenzyme A before then all of a sudden you're overworking your ALDH7A1, but it's actually being tied up in lipid peroxides. It's being tied up in making betaine. Then you won't make AAA. Then you're going to make P6C, and that's going to inactivate B6. And then you're going to have a worsening B6 deficiency because you took pantethine or pantothenic acid. So there's a hierarchy here. You want to work on your betaine intake either with foods or with a very low dose supplement. Low dose, I'm saying, because people take like 2 or 3 grams, and I think that might be too much in this situation. So again, because then you have to have more B2. It's like a cascade. So Chris Masterjohn does a good job with betaine. He says between around 250 for kids and 500 for adults. You should always check your plasma amino acid test before you start betaine, if possible, because high methionine levels plus betaine equals potentially brain edema. So, all right. So here's some more thoughts that I had about this pathway. There's an overactivation of pyruvate dehydrogenase complex, and that leads to the depletion of thiamine lipoate and pantothenic acid. And then that can lead to a buildup of pyruvate. So see this block here. If you have a buildup of pyruvate, then I'm reading what I wrote over here. Competition for phosphoglycerate dehydrogenase can lead to low serine production from glucose. Okay, yeah, that makes sense. So that's over here. So if you have high pyruvate levels, there's different places that it can go. Okay, so one, you could be pushing it to lactate, but if you have problems with oxalate, maybe you are stuck in this hyperoxaluria pathway, then you're going to struggle with this. So your pyruvate's not going to go that direction. Your pyruvate can become acetate. Acetate is one of the acids that is suspect in helping to make anhydroretinol, but we make acetate all the time. I think the acetate would probably be caused by excess hydrogen peroxide, and not because of alpha ketoglutarate dehydrogenase activity or pyruvate dehydrogenase complex activity, because both of these would be shut down. So it's just the hydrogen peroxide that's causing the pyruvate to go to acetate. Another place that pyruvate can go is to alanine. So sometimes on labs, we only see rises in ALT, but not AST. And so it's potentially that your liver enzyme is going up because you're pushing for pyruvate to alanine with the alanine aminotransferase enzyme. Pyruvate can also go to it can go to oxaloacetate, but most of the time people have a block in pyruvate carboxylase, and that's because alpha ketoglutarate blocks right here. Here is the phosphoglycerate dehydrogenase. It's an enzyme that goes from isocitrate to alpha ketoglutarate. I think that there's a backlog here because there's a inhibition of alpha ketoglutarate dehydrogenase because of reactive oxygen species. So then this enzyme over here is having a lot of competition going back and forth between alpha ketoglutarate and isocitrate. And so then because that enzyme is tied up, then glucose isn't made into serine and you have low serine levels. There are a lot of reasons for low serine levels, like it could be a B6 issue. So it takes a little working around to figure out what's going on. And then pyruvate itself, another possibility is that pyruvate can go to the peroxisome and become hydroxypyruvate. So that could actually lead to low serine levels as well, because you're sucking up serine into making hydroxypyruvate, which I believe that scenario leads to oxalate formation. And then your glucose, another possibility is that because of all the oxidative stress, you could actually be shuttling some of your glucose off to the pentose phosphate shunt pathway, and then that would actually lead you to less pyruvate, right? So, and that's controlled somewhat by dehydroascorbic acid levels. One more spot. Pyruvate to malate is another potential reaction. And then here again, there's that phosphoglycerate dehydrogenase. This enzyme has 3 roles. It helps to make serine from glucose, but it also works these 2 enzymes in the TCA cycle, or it is 2 enzymes in the TCA cycle. And the interesting thing is that I believe because your TCA cycle is shut down, and you're basically reliant on glucose at this point to make some ATP. There's one part of this pathway is that you end up with more of like a reactive hypoglycemia, and you put pressure on this phosphoglycerate dehydrogenase complex because the malate has to go to oxaloacetate. And then it eventually will actually come out here. I don't show it here, but it is what gives you another source of gluconeogenesis. So lots of interactions here. Yeah, that's the original map. So I want to talk about the oxalate thing briefly. I want to do a whole video on this, but I want to tell you my theory about low serine levels. If you have low serine levels and you have hyperoxaluria, I think this is what is causing it. So when you have excess pyruvate, maybe because you have a lack of coenzyme A, you've been depleted of your pantothenic acid from having overactive pyruvate dehydrogenase complex, or potentially now you have a thiamine deficiency, and that's leading to high levels of pyruvate. Then pyruvate is shuttled into the peroxisome. Remember, I said there's like those different pathways that it can go. It gets shuttled into the peroxisome. It sucks up your serine. It becomes alanine, and also hydroxypyruvate is the other byproduct of this reaction. It's B6 dependent. And in my own family, there was some severe hyperoxaluria going on. And so, the first thing you do is, B6, because if you need B6 so that you can go from a glyoxylate to glycine. That makes sense, right? Oh, yeah. We want to take our glyoxylate and go to glycine because glyoxylate becomes oxalate. So B6 will solve everything. It didn't solve anything. One, I think there was a functional B6 thing going on, but 2, even if you surpass the P6C levels that's binding to the B6, 2 is you restored this enzyme. So if you restore AGT, it works 2 different reactions. If you make more hydroxypyruvate from your excess pyruvate, then you're using the enzyme GRHPR, and it makes deglycerate and L-glycerate. But GRHPR is a moonlighting enzyme, and it not only metabolizes hydroxypyruvate in the cytosol, but it also metabolizes glyoxylate to glycolate. if you are tying up HPR over here, dealing with excess hydroxypyruvate, then your glyoxylate is going to become oxalate. And then oxalate inhibits lactate dehydrogenase. And then that can lead to being stuck either way. Lactate or pyruvate can lead to being stuck here at this particular thing. And this is a pivotal area where you recycle NAD. And if you are, let's see, if you are stuck in a high pyruvate state, which seems to be happening, then you aren't making NAD or recycling NAD, and then you can't deal with vitamin A. And that's how your retinol levels, your retinaldehyde levels go up and your serum A goes up one way. Anyway, so that's what I think is happening. And I hope to make another video on that, but there are actual studies showing that they give healthy people B6 and suddenly they're making oxalate. Potentially this is why. Maybe they're upregulating this enzyme. Maybe they don't have enough coenzyme A and they have high levels of pyruvate. It's totally possible. Let's see, what am I saying here? Oh, I was talking about the serine. So a problem with sucking up your serine and dealing with excess pyruvate is that your serine is not going to be available for making glycine and then glutathione. Also, your serine is not going to be able to help you make glutathione peroxidase. So that's a bust, right? So you got to be careful. How do you even be careful with that? Well, if you find out that your oxalate levels are sky high on your oat test, like super duper sky high, then probably a low carb diet would be a benefit for a bit, because then you would have less glucose to pyruvate, right? But also you could have less serine levels too. And then that's an issue because, you know, serine is involved in the freeing of ethanolamine and choline to make plasmalogens. There's so many things in this pathway. So here's one of my sweet friends. She let me share her labs, and here is her oxalate level. And I think this is kind of what had happened for her, is that she was struggling with this. I think she probably struggled with anhydroretinol, and it triggered massive depletions of micronutrients and then a buildup of pyruvate. And then she was shuttling pyruvate off into the peroxisome. And here is her serine level. So I mean, that's just one possibility that's been happening. And you can see that there's other evidence in this pathway that she did. You know, I don't know if she's still struggling with anhydroretinol. Potentially she is. And so you can see that there's low levels of B3, B6, folate, pantothenic acid, biotin, serine's very low. Choline is kind of marginal. She actually supplements with choline bitartrate. And then the inositol is a bit low too, which, you know, we need the phosphatidylinositol uses phosphatidyl. Is it the ethanolamine? I think it is. Okay. Okay, I already said that the pyruvate may result in depletion of the amino acid serine, and then there's like a moonlighting, and I do hope to do a little bit more on hyperoxaluria. So what about dopamine, norepinephrine, serotonin dysregulation, and histamine intolerance that I talked about at the beginning of this video for the shorter part of it? Is it due to monoamine transporter 2 disruption? I think so. So we actually make plasmalogens in our brains too. This slide is just showing that we will make we metabolize phosphatidylethanolamine and phosphatidylcholine. Okay. So what about monoamine transporters? So this study shows that a reduction of monoamine transporters, such as I showed a reduction of monoamine neurotransmitters such as dopamine, norepinephrine, and serotonin in these knockout mice, and they ended up having a hyperactive phenotype with deficient social interaction. And the coworkers showed correlations between plasmalogens and brain neurotransmitter levels, as well as hyperactivity phenotype in these special knockout mice. These knockout mice are not able to make plasmalogens. So they believe that the underlying reduction of the neurotransmitters isn't totally defined yet, but they think that it's an impaired homeostasis of plasmalogens, which leads to a low expression of monoamine transporter 2. And it's a transporter of monoamine neurotransmitters from the cytosol into the synaptic vesicles, okay? So they actually gave these animals a plasmalogen analog. Oops, I put all these things on here and I forgot. A plasmalogen analog, and that it helped with the hyperactivity, but they didn't see changes in the plasmalogen levels in the cortex and cerebellum, but they're still pretty sure that fixing the somehow the plasmalogens helped the transporters. So based on that, I was just thinking about how the presentation of people, they're all struggling with neurotransmitters. Everyone I know is struggling mentally, and that's so hard. My heart breaks because one, I always tell people that this isn't your fault. This is biochemistry. Don't get in your head about it just because you feel a little wiggy or angry. That's not your personality. That's biochemistry. Now, once you fix the biochemistry, could you still have the behavior? Yes, because behavior is actually making a mind map for some type of thing that you're doing. Okay. And so you can get stuck in a behavior even though the biochemical part is gone. And that's what happens in autism. We can fix the biochemistry, but the behaviors that have been laid down, it takes a while for them to resolve. And so what I will see in my clients, that if we're fixing their biochemistry, and so perhaps they have a cover their ears and scream behavior when a certain thing happens, like for my daughter, when she intentionally turns the Wi-Fi off on her iPad, intentionally, she will cover her ears and scream. But we've been working on biochemistry, and now she'll do it and she'll cover her ears and she'll gently scream because the force of the chemistry behind it is not there anymore. That's great, right? And then we can talk about the behavior because she's not in the biochemistry. She's not having the crazy hormone changes or the neurotransmitter issues. Okay, so this is about histamine, and histamine plays an important role in as a neurotransmitter. So not all histamine is bad. It's kind of like another Goldilocks thing. But histamine N-methyltransferase is an enzyme in the central nervous system that metabolizes histamine, but it's in the cytosol of a cell. It's not in the outside, so you have to transport histamine across the cell membrane. And to do that, you need a monoamine transporter or an organic cation transporter. And we've already shown that the literature shows that plasmalogens help with transport, right? We know that. So what if histamine reactions are, one, high retinol levels in the blood because of problems with, metabolism that triggers a mast cell reaction. We know that. Also, I think that lack of PKC delta, because you're constantly having to make these new baby mitochondria and you're lowering your PKC delta pool, causes mast cell degranulation. Well, now you have all this histamine floating around, but you can't get rid of it no matter how many cofactors you consume, because you can't transport it into the cell where the machinery is to break it down. And that's because of plasmalogens. Yeah. Okay. So what are some symptoms of low levels of MAT2 transport and potentially dopamine dysregulation? Lack of motivation, fatigue, mood swings, anxiety, lack of pleasure, depressed, hopeless, low sex drive, trouble sleeping, restless legs, disturbed sleep, short-term memory deficit, can't think of what you just said a few minutes ago. By the way, I'm doing better. So, and then constipation. Those are all signs of dopamine dysregulation. So if you have high dopamine levels, is it it could be you're struggling with like dopamine beta hydroxylase, which is inhibited by Candida and also is a copper dependent enzyme. So maybe it is that. But what if it's that you are struggling with transport? It could be that also. Here's some more symptoms. Parkinson's-like symptoms like hand tremors or other tremors at rest, loss of balance or coordination, increased muscle limb stiffness. I have one client who has never been able to touch their toes in their whole life and now is flexible. Tried stretching millions of times, like couldn't complete a stretching program because the pain was so bad. That's increased muscle limb stiffness. Muscle cramps, like cramping up hands, that's a sign of low plasmalogen or a sign of dopamine dysregulation. Attention deficit hyperactivity disorder, problems with anger, like low self-esteem, maybe attacking other people on social media because, you know, you feel like they're trying to get all up in your business and think, I don't know, maybe that's a thing. Maybe that's a sign of dopamine dysregulation. If you're struggling with low self-esteem, maybe you're angry at the person for, you know, overstepping their boundaries. Man, everyone on Facebook has dopamine dysregulation. Okay. Impulsiveness, like if you have impulsive behavior, lack of organizational skills, poor concentration. Schizophrenia is definitely dopamine dysregulation. Social withdrawal, like you just don't want to be around people. You could have a flat effect, reduced motions, finding no pleasure in life, just like really humdrum, right? Okay. Okay, what about norepinephrine dysregulation? Well, if you're struggling with transporting norepinephrine, you might have anxiety or depression, again, attention deficit disorder, headaches, memory problems, sleeping problems, low blood pressure, like hypotension. So maybe this is a POTS thing. Postural orthostatic tachycardia syndrome could be struggling with plasmalogens, low blood sugar. You could that could be also a problem with norepinephrine, and then changes in blood pressure and heart rate. So if you have tachycardia, it could be a norepinephrine issue as well. So you go from dopamine to norepinephrine with dopamine beta hydroxylase, and it could be, like I said, copper deficiency or maybe Candida. And so then you would have low levels of norepinephrine. One of the signs of low levels of norepinephrine is extreme pain. Like you just have horrible pain levels. So what about serotonin? What would be the signs that you're struggling with serotonin transport? You might have anxiety or depressed mood or aggression, impulsive behavior, insomnia, dementia, and cognitive decline. It's associated with obsessive compulsive disorder, panic disorder, suicidal behaviors, post-traumatic stress disorder, social anxiety disorder. All of these things are related to having problems with serotonin. And low serotonin can cause obesity, diabetes, cardiovascular disease, fatigue, osteoporosis, gastrointestinal issues, including irritable bowel syndrome. So some of you are probably like, I have all of these symptoms. If you have all of these symptoms, then likely you have plasmalogen issues, right? What about very low cholesterol levels? It's not a sign of good health. We need cholesterol. We need it. We need it to make steroid hormones. We need it for brain health. So it's a sign of dysregulation of plasmalogen production. It means that there's a lot of things wrong, and we could go back and look at all of the cofactors and stuff. So interestingly, this study shows that both high and low plasmalogen cells have lower cholesterol synthesis. So again, you have to go back and think about the person. Like, what is this person going to have a high plasmalogen state, or do they have symptoms of maybe potentially having a plasmalogen deficiency? So if their diet is low in choline, let's just say that they have a very limited diet. They don't have a lot of micronutrient sources and they're not supplementing. Most likely they have a plasmalogen deficit. This person might crave physical activity because physical activity would help to upregulate plasmalogen production. And so, you know, they might need to exercise to feel good because that frees cholesterol and helps them to make DHAP. And remember, I said that plasmalogens, the half-life is 30 minutes for, I think, for the choline one, and then 6 hours for the other one. So it's like they're craving the physical activity to feel better in the brain because it helps them to restore lipid membranes and restore the capacity to do neurotransmitters. It's really amazing. I'm so fascinated by this subject. So here is this highlighted area. That's the plasmalogen. And so if, so how do I say it? So if you have plasmalogen deficiency, you are going to be struggling with making cholesterol, because you have to have the plasmalogen to make the VLDL cholesterol molecule. So that's important. But also, if you are making too much lipids, you can see that it's going to suck up your plasmalogens, right? So that's a big thing. We want to have a good balance. We don't want to be just making tons of lipids. And I do think that the methylfolate trap is a contributor, but also eventually I'll do a case study about this one client who has zinc toxicity and magnesium deficiency. And I think that that's contributing to hyperlipidemia. And then the gut dysbiosis. Oh my goodness, I could go on and on. I'm going to try to be brief about this because I think the gut-associated lymphoid tissue needs an entire other video. I do believe that anhydroretinol causes massive problems because you cannot make retinoic acid out of anhydroretinol, and we need retinoic acid to be able to differentiate from a monocyte to a macrophage. Macrophages are killers of bacteria and pathogens. So if you have high monocytes on your lab work, that's a huge sign that you're not making macrophages. That's a sign of retinoic acid deficiency. It's also a sign of Epstein-Barr virus. And do you know that EBV actually has an aldehyde dehydrogenase and it can metabolize vitamin A for you? So perhaps EBV is just a way for you to deal with your high vitamin A levels. It's a possibility. Maybe it's a symbiote. Anyway, you need retinoic acid to make a macrophage. You also, your dendritic cells metabolize vitamin A. So if you have anhydroretinol, your GI tract has no vitamin A to make retinoic acid if you have anhydroretinol, because it cannot become retinoic acid. So your dendritic cells use the retinoic acid and make retinoic acid, send it to your B lymphocytes, and your B lymphocytes make IgA and IgG, which helps to fight off gut pathogens. And check this out. Where do they study anhydroretinol at? Lymphocytes? No joke. So perhaps your gut dysbiosis is because anhydroretinol will kill a lymphocyte. Anyway, so gut dysbiosis, what that does is it causes the ethanolamine and choline steal and potentially serine as well, and that lowers your ethanolamine levels. So here are some of the nasty bugs that can do that. Clostridium, Listeria, Enterococcus escherichia, I guess is how you say it, Salmonella. And then this S. typhimurium. I'm sure there's more than this, but this is just one study that I found. My own daughter has an overgrowth of a constipating version of Clostridium. So no one wants to treat it because it's fine. She's not having diarrhea. It still produces toxins, people. It still produces toxins. So that's a big struggle. Interestingly, the ethanolamine is converted into acetaldehyde in ammonia. And then the acetaldehyde is then converted to ethanol. Ethanol plus an acid plus retinol is anhydroretinol. No joke. This says it's more likely to be converted into acetyl-CoA. Really? Maybe if you have enough coenzyme A, but I've already decided that's probably a bust, right? So, and then if you do make acetyl-CoA, you can use it to do numerous processes, like you could use Krebs cycle or a glyoxylate pass. That sets you up, right? That you could either make glycolate or you can make oxalates. It's just not a really good idea to have an unhealthy gut microbiome. And retinoic acid is needed to run the immune system. We can't discount all of the studies out there. Is too much retinoic acid bad? Yes, it is. It's not good either. So There's a whole regulation system inside our body, and probably some of us are dysregulated. Okay, so being able to use ethanolamine as a carbon nitrogen source is likely gives pathogenic bacteria a competitive advantage. So if you are a person who eats some eggs and you feel bad after you eat eggs, this is probably a gut microbiome issue. I mean, you could have an egg allergy. That's possible too. but it's probably a gut microbiome issue. You're probably getting high on acetaldehyde and ethanol. Zoe was struggling with this because Candida, just like those bad bacteria on that previous slide, Candida and other fungus, other yeast, not fungus, yeast. Well, I think fungus could do it too, but Candida will actually, no, I think I read that fungi. Oh no, here it is. Let's see. I don't know. I'll have to look it up, or you can look it up. Okay, so the Candida, they eat the ethanolamine and the choline, and they can steal serine too. And this is phosphatidic acid. This comes from, our diet, like eggs and stuff too. So gut microbiome, big issue, but I'm really kind of sad about it because I just never wanted to get into that. So there's so much more to explore. I really want to explore the gut-associated lymphoid tissue and retinoic acid's role in gut immune function, because I've had so many people bring me their stories that their kid suddenly had low IgA levels and low IgA levels in their stool. And that happened to my kiddo too. And how did it happen? Well, I had to pump. Also, I had Candida while I was breastfeeding, which means I probably made anhydroretinol. And then I was pumping, and I was fortifying her food, fortifying her milk with formula, because she was failure to thrive. My sweet Zoe was failure to thrive. And I believe that she only got anhydroretinol mostly. And that led to her IgA levels going low, and she was diagnosed with immunodeficiency. And then she developed a massive microbial problem. So there's a lot going on with her, and I could do a whole case study on my sweet girl. It's amazing that she's even here. She's a miracle. And I'd like to say this. Of course, I do want to do more on hyperoxaluria, have this sulfite intolerance pathway in my brain, histamine intolerance, kind of went over it today, and salicylate intolerance. I have a lot of plans to do things, but I need to say this. My child and all of my clients over the past 3 years that have genetic syndromes, and they're vulnerable to being broken more so than the average human being, they deserve honor. It's not like their parents didn't watch them. Their parents loved them. They fed them as well as they could. I'm a crunchy mom. I fed my kid all kinds of healthy foods. But because their metabolism is broken, they squeak those wheels. And those squeaky wheels are what's bringing about this information. If you squeak your wheel hard enough, then people can see it. If you almost die from brokenness, then we can see the pathways. So we need to honor those people. I'm not yelling at anybody who's watching this video. I'm just very passionate about that. So let's love on these people. Let's love on Olivia and Oasis and Zoe. And I can't name many more clients because, I haven't asked for permission to talk about them, but we need to love on them, and we need to thank them for their help. All right, that's it. This was a long video, but I hope you really enjoyed it, and have a great day.